Welcome to lecture 10 of our course on high performance computing. In the previous lecture, we had taken a look at a few more MIPS-1 instruction set features and started looking at the kind of hardware that would be involved in executing or processing the instructions as your program executes. And just referring you back to the last slide of the previous lecture, we were going to make three important assumptions in trying to understand the hardware. The first assumption is that we will assume that in the decisions regarding the hardware, activity which can be overlapped in time or done simultaneously. So, if there are two different steps in instruction execution which can be done at the same time, then the hardware for those two steps would be designed so that they could operate at the same time. We will assume that we are concerned only with a load store RISC instruction set. And finally, a big assumption, we will assume that even though main memory is about 2 orders of magnitude slower than the processor, we will assume that delays due to main memory are not typically seen during the execution of instructions by the processor, because otherwise that would dominate the execution of the amount of time for the execution of a program. And in fact, this is going to be, though initially we thought that this was an unrealistic assumption, we are told that if the processor contains something called a cache memory, then this is not an unrealistic assumption. So, we will go with these three assumptions. Now, one of the important concepts for us to have in mind before we can start looking at simple hardware to execute an instruction is the notion of processor cycle time. I had used this term earlier. In general, I had used the idea of the time scale of a processor when I had said that the time scale of a typical processor today is a couple of order of magnitudes finer than the time scale of current main memories. And I'll refer to the processor cycle time as the unit of that time scale. So, for example, when we talked about a somewhat slow processor today, we talked about it as having a unit of time scale of about 1 nanosecond. So, that was the ballpark kind of a number that we were talking about. In other words, 10 to the power of minus 9 seconds. Right? And more realistically, since now we are talking about the steps involved in executing an instruction, I'll refer to a processor cycle time as the amount of time required to do a very simple operation. A simple operation can be done in one cycle, and therefore, if many steps or simple operations must be done to execute an instruction, the amount of time to execute a single instruction will be multiple clock cycles. So, we have to have some idea of what kind of simple operation can be done in a single processor cycle. Now, let us look back at our sequence of steps involved in the execution of an instruction. So, there are the 4 steps described at the higher level. You need to fetch the instruction, you need to decode it, you need to do the operation involved, and you need to write back the result. Now, in each of these we had put some sub-steps. These are the more basic operations which are involved in executing the instruction. The entire sequence of steps is required to do the execution of one instruction. But let us look at these sub-steps. So, first there is IR equals memory of program counter. This is the step where the instruction was read out of memory. Now, with our third assumption that most of the time memory delays are not seen because of the cache memory present in the processor, due to which the instructions or data that are required by the processor are much of the time available at processor speed. So, rather than viewing that first step IR equals memory of program counter as being a multiple cycle operation, I can say that this is going to take the amount of time that it takes to do a cache memory access. Cache memory is something inside the processor, and therefore, the amount of time for the first step is the amount of time to do a cache memory access. It is inside the processor. What is the amount of time to increment the program counter? Incrementing the program counter involves reading the program counter, adding 4 to it for our MIPS-1 style RISC instruction set, and storing the sum back into the program counter. So, that is a simple ALU operation. I write it as a simple ALU operation because it merely involves addition by 4. It is much less complicated by a general signed ALU operation. Okay. We then come to decode. What is involved in decode? In the decode step, the fields of the instruction as it resides in the instruction register are examined by the hardware to determine what the operation is, what the operands are, and so on. And this is going to be implemented using some very simple circuitry. well, even if it's not simple, so some amount of circuitry. Now the way that I'm describing this over here is using the term logic circuitry, and that's a somewhat in some cases people may even describe it as simple logic or just logic. The term logic is coming from the fact that the electronic circuits that are used for this or for purposes like this are made out of very, at the lowest level one can view them as implementing functions of logic gates, AND gate, OR gate, inverter, etc. Therefore the term logic circuitry has come to be used. So in order to do the decode, some small amount of, or some amount of logic circuitry is going to be involved. To get the operands from registers, it just takes the amount of time to access the registers. There are about 32 registers in the processor based on our current assumption. What about the next step in executing the operation? The appropriate functional hardware has to be triggered and the operation has to be done. So for example, if this is an add instruction, then the ALU has to be triggered and the add operation has to be done. So that's the time involved in that is the amount of time for the ALU operation. On the other hand, if it's a load or store, then the data has to be either read from in the case of a load or written to in the case of a store memory. Again, with our third assumption, we're no longer talking about a memory delay but about a cache memory access time. And finally, writing the result back to the destination register takes a register access time. So now looking at these sub-steps in the execution of an instruction, we realize that each of them involves a memory access, none of them involves a memory access, each of them involves an operation inside the processor, and we could possibly try to simplistically view these as the determinants of what a cycle, the amount of time for a processor cycle might be. In other words, we might say that a processor cycle is the amount of time in which any one of these primitive steps, the simple operations in the execution of an instruction might take place. In other words, the amount of time for a cache memory access, or the amount of time for an ALU operation, or the amount of time for a register access, maybe along with some simple logic like decode. Since the amount of time for a register access is likely to be much smaller, much less than the amount of time for an ALU operation, or definitely much less than the time for a cache memory access. So with this kind of assumption of what it means, what processor cycle time means, we can look back at the basic steps and try to count the amount of time that it would take to execute any one instruction in terms of processor cycles. Right? And we think of a processor cycle as being like that 1 nanosecond. So we can actually count or associate time intervals or nanosecond counts with execution of instructions. So let's go back to the slide with the steps in the execution of an instruction. So we were going to assume that IR memory of program counter would take one cache access time, and incrementing the program counter was a simple ALU operation. And we saw that these two could be done in parallel. Therefore, the amount of time to do the instruction fetch we will view as being one cycle. The amount of time to do the cache access would have been one cycle. The amount of time to do the simple ALU op would have been one more cycle, which is why we had showed it as two lines in our previous listing of the operations. But bearing in mind our first assumption, which was that things which can be done overlapped in time will be done overlapped in time. So I'm indicating over here that these two operations could actually be done in parallel as per our earlier discussion, and therefore we account one cycle against those two operations. Similarly, we had also discussed and I think sort of realized that the decoding of the instruction and the fetching of the operands from registers might also be done in parallel and could therefore be accounted as being just one cycle. However, in the third major step of instruction execution, there was triggering the appropriate functional hardware such as an ALU operation, and in addition to that the cache access. And unfortunately these two operations cannot be overlapped. Why can they not be overlapped? The reason they cannot be overlapped is, consider the load store instruction. Let's say a load instruction. So a load instruction could look something like this. So you'll notice that as far as the load instruction is concerned, it gets fetched in that one cycle, it gets decoded and its operands get fetched in one cycle. What does it mean for its operands to get fetched? That basically means that the value in R29 will be available, and that's what its operands fetched means. Subsequently, the appropriate functional hardware has to be triggered. Now we don't normally think of this load instruction as requiring an ALU or a floating point multiplier or anything, but when we realize that there is a need for an addition in order to implement the effective address calculation, in other words adding the contents of R29 to -4, then we do realize that something like an ALU operation is required in order to calculate the address which is supposed to be sent to the cache memory in order for the cache access to take place. Therefore, we do need to account one cycle for the appropriate functional hardware and one cycle for the cache access, even in the case of a load instruction, which is why I show one cycle for each in this more detailed enumeration of the amount of time for execution of an instruction. The final step is writing the result to a destination register, which is equivalent to the amount of time for a register access, which we had accounted as part of the definition of one cycle. So now let's look at a few different examples of MIPS1 instructions and try to see how much time that particular instruction would take. Let's start by looking at a jump register instruction. And for each step of the sequence, we're going to ask, does the jump register R6 instruction need that functionality to happen? So for example, we ask, does the jump register R6 instruction need to be fetched? And the answer is yes. So I'll circle the one cycle. That one cycle will have to, the hardware associated with that one cycle will have to execute for the jump register R6 instruction to be executed. Does it have to be decoded and its operands fetched? The answer once again is yes. It has to be decoded, and certainly the value of R6 must be fetched from the register file. Is there any functional hardware to be triggered, or is there a need for any load or store to be done from the cache memory? The answer is no. And therefore, we don't account either this cycle or this cycle against the execution of a jump register R6. Finally, does a destination register have to be written? And the answer is yes, because we realize that as far as this register, as jump register R6 is concerned, the primary effect of this register is to change the program counter to the contents of R6, and that is therefore an integral, that is basically very important as far as this instruction is concerned. So looking at the accounting that has been done, we realize that the jump register R6 could execute in 3 cycles. It doesn't require all of these steps to take place, but it does require steps amounting to 3 cycles to take place in order for it to be executed. Let's look at another example. Consider the instruction add R1, R2, R3, one of our more popular, frequently occurring examples. So does it have to be fetched? The answer is yes. So that's one cycle. Does it have to be decoded and its operands fetched? Yes, certainly. Its operands are the values in registers R2 and R3. So this we account as another cycle. Does any functional hardware have to be triggered as far as this instruction is concerned? Yes, certainly, because it's an add instruction. Therefore, the ALU has to do the addition. So that cycle has to be accounted. Does data have to be fetched or written into the cache memory? The answer is no. Therefore, we don't account this cycle. Does the destination register have to be written? The answer is yes. R1 is the destination register. So we account this cycle. And when we do the accounting, we see that the add R1, R2, R3 instruction will take 4 cycles to execute. It doesn't require the 5th cycle, which was necessary only for this load or store instruction. Okay. So just to remind you, the jump register R6 instruction we accounted as taking 3 cycles. The add R1, R2, R3 instruction we account as taking 4 cycles. One more example. Consider the load word R1 -8 R29 instruction. Does it have to be fetched? Yeah, this one cycle is going to be accounted against all instructions, as is the second cycle, because whatever the instruction is, it does have to be fetched from the cache, and it certainly has to be decoded and its operands fetched. Okay. Now, is there any functional hardware that has to be triggered as far as this instruction is concerned? We have just seen in 1 or 2 slides ago that there is the need for an ALU operation as part of calculating the effective address, the contents of R29 added to the assigned displacement, and therefore we do have to account that one cycle. Next, is there a need to account a cycle against the load or store in terms of access to the cache memory? This is a load instruction, therefore there's certainly the need for accounting that one cycle. And finally, is there a destination register to be written? Yes, there is. R1 has to be written. And therefore, when we do the accounting, we see that this particular instruction, the load word instruction of the MIPS1 instruction set, based on our set of assumptions, regard the 3 assumptions as well as our assumptions about accounting of what can be done in one cycle, will take 5 cycles to execute. So the jump register R6 instruction took 3 cycles, the add R1, R2, R3 instruction took 4 cycles, and the load word instruction is accounted as taking 5 cycles. Right? So in general, you could go through this exercise for all the MIPS1 instructions that we have seen, and you would find that based on our three assumptions and the assumptions regarding the definition of a cycle, any of the instructions would take something between 3 to 5 cycles. The jump register R6 takes the minimum, only 3 cycles, and the load word instruction takes the maximum, 5 cycles. All the other instructions are either 3, 4, or 5. Now, and over here, this is a listing of the 3 examples that we have seen, the kind of terminology we might use. In referring to the fetching of the instruction, I might use the term ifetch, standing for instruction fetch, the 1 cycle for that. In terms of decoding the instruction and fetching its operands in parallel, I might use the term decode/operand fetch. And in terms of doing the operation, I might use the abbreviation doop. These are not standard abbreviations, they're just abbreviations which I will use. In addition to that, I might talk about write read for writing the destination register, and then this step of effective address calculation, which was necessary only for the load and store instructions. In our particular MIPS1 instruction set, the addition of the base register value to the signed displacement. So the bottom line is any of the MIPS1 instructions can be executed in somewhere between 3 to 5 cycles. Okay. Now, as a little bit of an aside, the question that arises now is, we had made certain assumptions, not we, but the people who designed the MIPS instruction set had made certain assumptions regarding, for example, the choice of addressing modes. And how critical were those assumptions looking back? Now, let's just make a hypothetical assumption. Let's suppose that the people who designed the MIPS instruction set had decided that it was not worth having the base displacement addressing mode, but had decided instead to only have the register indirect addressing mode. You'll remember that the register indirect addressing mode is an addressing mode where the address of the memory operand is contained inside a register. It is superficially similar to the base displacement addressing mode, and is in fact a special case of the base displacement addressing mode where the value of the displacement is 0. In other words, nothing has to be added to the destination register. To the base register. Now, the people who designed the MIPS instruction set architecture could easily have opted to have only the register indirect addressing mode. And what if they had made this assumption? Now, if they had made this assumption, looking at the sequence of cycles that were associated with the different operations in our instruction set, we realized that the impact would have been only on the load and store instructions, and specifically, there would not have been the need for effective address calculation. There would no longer be the need to add the displacement to the value in the base register, since the displacement is 0. And therefore, there would not be the need for the cycle for effective address calculation, the ALU operation of calculating the address of the memory operand. And therefore, the impact on our table on the screen would have been that there would have been no instruction which required 5 cycles. Instructions would require either 3 cycles or 4 cycles. In other words, you might say programs would have executed faster if they had not had if instead of having the base displacement addressing mode, they had just had the simpler register indirect addressing mode. Now, this is of course not a complete argument, because you have to also consider what would have happened if they had left out the base displacement addressing mode and had included only the register indirect addressing mode. Would there have been more instructions required in the program in order to achieve the same effect? And you may want to look at it this way. In situations where there was a base displacement addressing mode, such as a situation where there was a load word instruction R1 -4 R29, this could have been as a result of something like our local variable access inside a function call. That may be where this addressing mode came from. This may have been an instruction which is loading a local variable x into register R1. Now, what if we didn't have the base displacement addressing mode? Then in order to generate the address of the local variable x, we would have had to have an instruction which would modify the value of R29. And what would that instruction be? That instruction would be a subtract instruction. Subtract 4 from R29. And then the load word instruction could just use R29 with a displacement of 0. So we would have had to have an additional instruction in our program if the base displacement addressing mode was not available. And therefore, even though the amount of time to execute the load instruction would have gone down by 1 cycle, we would have had one more instruction which would take an additional 4 cycles. Which is why the decision about whether having the base displacement addressing mode or not cannot just be taken into account based on the cycle count that results for a single instruction, but must take into account the impact on entire programs. And that is why we will stick with the MIPS-1 designer's idea of having the base displacement addressing mode. But this discussion was interesting in that it reveals some of the kind of thinking that might have to go into account in designing an instruction set architecture. Okay, now moving right ahead, we can get into the specifics of what happens when an instruction executes. Now let's first go through the first step of instruction execution. So the objective is, and I'll refer to this as instruction fetch, and instead of abbreviating it as only as ifetch, I'll abbreviate it now as if, just to save space. So if stands for instruction fetch. It is the part of the processing of an instruction where the program counter is sent to the memory responds with the instruction is written into the instruction register, and in addition the program counter gets incremented. So what kind of hardware is going to be involved in doing this? Remember that the steps involved are these two: send the program counter value to memory or cache as the case may be. Memory will respond with the instruction which is stored into the instruction register and the incrementing of the program counter. So over here what I am depicting is there is one box which is the program counter, and the arrow which is shown pointing from the program counter to memory indicates that the program, in this particular example we might be talking about cache memory. So the value in the program counter is routed to the cache memory. That is the first thing to note. Subsequently the cache memory operation happens and the instruction goes from the cache memory into the instruction register. In parallel with this, the program counter value is sent to an adder along with the value 4, since that is the value of the increment, and the value is sent to another register called the new program counter. Now you will notice here that in this, technically what I have shown you over here is a very simplified version of a piece of hardware. It is showing you registers, it is showing you units of memory. So PC is a register, IR is a register. The adder that I am showing you is something like a very simple ALU, so it is a piece of hardware. The constant 4 can be generated and sent as one of its inputs. In addition, I am showing you another register I have never talked about before called the NPC, which we can now understand must be the new program counter. And the idea seems to be that rather than modifying the program counter directly, the register called the program counter directly, in this discussion we are going to assume that the program counter itself may get modified either later or at the same time, but we are assuming that the value of the incremented program counter is available in another register called the new program counter. So this is sort of a form of pseudo hardware. You talk about pseudo code to describe software. Here we have a form of pseudo hardware to understand what the hardware is doing. And this is basically all the hardware involved with instruction fetch. We can now move on to the second. You will notice that these two activities are shown as happening in parallel because the value in the program counter simultaneously goes to the adder for increment and to the cache memory for lookup in order to fetch the instruction. So the parallelism, the overlap in activity is implicitly being described. Okay, so we now move on to the next step. This was instruction fetch. The next step in instruction execution was the one where the instruction is decoded and its operands are fetched. And I am showing you the instruction fetch hardware to the left because the instruction register which contains the instruction after it has been fetched is going to be the beginning of our second step of execution, because the decoding of the instruction must examine the instruction register. Right, so I am not going to show logic which implements the decoding, since it is some kind of circuitry and we do not have any mechanism to talk about what the circuitry does explicitly, and therefore there is no point in showing a block which does that. But there is going to be circuitry which does that in the control hardware. We will concentrate more on the operand fetch, and we realize that for the instructions that we are concerned about, the operands are being fetched from the register file. So I will show the register file. In terms of this kind of functionality. Now for the particular kinds of instructions which we have, for example consider the arithmetic and logical instructions, the kinds of operands which may have to be obtained are, there is a possibility that there are two source operands, in which case two values will have to be read out of the register file. There is also the possibility that one of the operands is going to be an immediate value, in which case there is a possibility of the operand having to come out of the instruction register. So in the diagram that is to be shown to the right, we are actually going to show a register file. We are going to show a register file, okay, and the input to the register file. So, the information from the instruction register gets routed to the register file. What kind of information? Inside the instruction register, you will remember, is the instruction, and we know the format of the instruction from the discussion of the instruction set architecture. Therefore, there is a field in the instruction which identifies the first source register identity. There is a field in the instruction which identifies the second source register identity. Therefore, those fields from the instruction are sent to the register file. And in the register file, the hardware is built so that it reads the first source operand out of the register, appropriate register, and puts that value into a new special purpose register called register A, which is what was indicated by the first step in this sequence. Similarly, the second source register is read from among the registers as identified from its value in the instruction register and read into the register called register B. So, A and B are special purpose registers, as a result of which values which are operands will be read out of the register file. See, and that will handle the case of an instruction like add R1, R2, R3. At the end of this sequence of events, A will contain the value of R2 and B will contain the value of R3. Both have come out of the register file. Now, what about the example of add immediate? Add R1, R2 minus 6. Now, the value R2 will come as it did in the case of the first example into register A. But what about the value minus 6? The answer is minus 6 is a value which is present inside the instruction. And there is a path from the instruction to this sign extension hardware into a register called IM, another special purpose register. And the special purpose register called IMM contains the sign extended version of the bits inside the instruction which contain the immediate field. The net effect is that whatever kind of instruction it might be, at the end of this second stage of instruction execution, A will contain the first source operand, if there is any, B will contain the second source operand out of the register, if there is any, and the special purpose register called IM will contain the immediate operand, if there is any, as far as this instruction is concerned. Now, the concern which you may have is, what if the instruction which is currently being decoded and operands fetched is an add instruction? Then I agree that its first source operand will be available in special purpose register A, and its second source operand will be available in special purpose register B. But something will also be available in the immediate register as far as this instruction is concerned, and this instruction has no immediate operand. The answer to that question is, even if there is a value in the immediate register as far as the instruction is concerned, as long as we don't use it in the addition, no harm is done. But we are here able to do a piece of hardware or implement a piece of hardware which will do the same thing regardless of whether the instruction is an add or an add-I, and therefore we are simplifying the hardware. There is no necessity to use all three of A, B and IM in the step that follows. Based on the information that came out of decoded the instruction, either A and B can be used or A and IM can be used. In other words, for the add instruction, A and B will be used, and for the add immediate instruction, A and IM will be used in the addition that is to follow. Okay, so let's move on to the next instruction and the next stage of the instruction execution. Right now, the next stage of the instruction execution I'm going to label, let me just go back and say that I'm going to, from now on, label the second stage of instruction execution as ID, as an abbreviation of instruction decode and operand fetch. Now, in the next stage of execution, we had this requirement to trigger the functionality of the required functional unit, and therefore I'll just from now on talk of this as the execute or the EX stage. This is where the core execution of the instruction takes place. And our primary example is one where the piece of hardware that has to be triggered is the ALU. Without loss of generality, we may be talking about triggering a floating point adder or a floating point multiplier or some other piece of hardware, but the situation would be parallel to the one that we are describing here. Okay, so there are a few cases that we have to consider, since there are different kinds of instructions which may require the triggering of the ALU. We've already seen that arithmetic instructions obviously require triggering of the ALU, and that even load store instructions require triggering of the ALU in the MIPS1 instruction set for the effective address calculation. In other words, the addition of the base register to the displacement. Okay. So, for the arithmetic instruction, we know that what has to happen is, if it is a arithmetic instruction without immediates, then we want the value to be taken from register A and we want second operand to be taken from register B. On the other hand, if this is an arithmetic instruction with an immediate operand, then we want the first operand to be taken out of register A and the second operand to be taken out of register M. Remember that A, B and M are the special purpose registers into which these operand values had been loaded in the previous step, in our ID step of instruction execution. Okay. And what are the other possibilities we have to look at? We will come to that shortly. Alright, so we talked about the A, B and the M registers. We are now seeing that as far as the input to the ALU is concerned, the upper input is always coming out of register A, because that is the case for both the add instruction and for the add immediate instruction. But the lower input comes either from B or from M, and this piece of hardware over here has to be a piece of hardware which can be controlled by the decode hardware in the previous stage, so that the appropriate selection is made between B or M and only one of them goes to the ALU. So, in the previous stage there was logic circuitry which was decoding the instruction, and part of that logic circuitry would trigger this particular piece of hardware to select the correct one from among B and M as the second input to the ALU. The net effect is that the correct input, either A and B or A and M, will go to the ALU will be triggered to do the operation and will write its output, in other words the result of the addition or whatever the operation may be. The operation could be subtraction, it could be a logical operation, into another special purpose register called ALU out, standing for output from the ALU. And this sort of explains the notation that we had used over here. ALU out is the name of another special purpose register that we are assuming is present inside the hardware and used by the control hardware of the CPU. Okay, so much for the arithmetic instruction. What about the load store instruction? Now, in the case of the load store instruction, we remember that the need for using the ALU comes from examples like -8 R29. So, we realize that the R29 value is going to come through the A input, but where is the -8 value going to come from? If you go back to the previous slide, you will realize that the -8 value is going to come from the immediate register, because we'll go back to that slide. If you recall, the load and store instructions use the format in which there is a 16-bit field, the I format, and therefore in the I format the 16-bit field will be pulled out, sign extended, and is therefore available in the immediate register, and that will be the immediate value, which is the displacement value in the case of the load store instruction. So, for load stores, what we want is the value of the A register, which is the base register, to be added to the displacement value which is present in the immediate register, and that is what happens, and the appropriate value gets written into ALU out, and from there it can be sent to the cache memory or the main memory for accessing the data or storing the data. Right. In addition, if we are talking about a store instruction, the calculation of this kind will have to be done, but you will recall that for the store instruction things are the other way around. We actually want to store into the memory address, which is being indicated by the base displacement addressing mode, the value which is inside the register R7. So, where is the value of R7 going to come from? And the answer is the value R7 is going to come from the B register, if you look at the format of the instructions and the way that we are doing things, which is why I show a line going from the B register to the next stage of instruction execution, which is the one where the updating of memory is going to take place. So, as far as the load or store instruction is concerned, ALU out will contain the effective address, in other words the effect of subtracting 8 from R29, and the other arrow down here is going to contain the store data coming out of the B register. Okay, now there is a third situation that has to be taken into account here in terms of how the hardware is going to be used by the instructions, and that is the case of the branch instruction. Recall that in the MIPS1 instruction set, the branch instruction, such as branch if equal R1 R2 minus 16, uses a PC relative addressing mode. and therefore there is a need for some kind of calculation to take place to calculate the target address as far as the branch instruction is concerned. Okay, now the value of the -16 is going to be available in the immediate register, because if you remember the format of the instruction that is used, -16 is a value that will be stored in the 16-bit displacement field or immediate field of the I format. But in the case of the branch BEQ instruction, what we need to modify is not the register R1 or the register R2, but the program counter. And therefore we need to get into the upper input of the ALU. Into the lower input of the ALU you want to get immediate, which is going to be the equivalent of this PC relative displacement. But as far as the upper input of the ALU is concerned, we want to get something related to the program counter. And that is the reason that we had this additional selection hardware available at the upper input of the ALU. So what will go into the upper input of the ALU is the value from the register that we had called NPC in the previous step. So in the previous step, if the decode hardware had understood that this is a branch instruction, then it will trigger this piece of hardware to send not A but the NPC value as the upper input to the ALU, and the net effect is going to be that the 16-bit PC relative displacement is going to get added to NPC. And you remember that NPC is PC plus 4, and we now begin to understand why the branch instructions talk about PC plus 4 minus 16, because in our implementation we are going to assume that rather than using the PC value in the computation of the effective address or the target address, they are going to use the value of PC plus 4, which is available in NPC, and we are referring to PC as the value of the address of the instruction which is being executed. Right. So hence we show a path from NPC into the adder as well. Now as far as the branch instruction is concerned, there is a need to also generate during this step of execution a check of whether the condition that is being evaluated is true or false. So is R1 equal to R2 or is it not? And therefore we show an additional piece of hardware which can check for comparison with 0 or comparison between two registers, and set a register which we will call the condition register. Therefore at the end of this piece of this step of the instruction execution, we have an additional register called cond or condition, which will either contain the value 1 for true or the value 0 for false, which will be used in subsequent steps of instruction execution to either change the value of the program counter towards the target address, which is available at the output of the ALU, or not to change the value of the target address. And similarly for the jump instruction. Okay, so this is what has to happen in the case of instruction execution. Now I should comment that in the case of the jump instruction, not much activity has to happen other than the concatenation of bits from the instruction register, which will be routed directly along with 2 zeros along with bits from the NPC, and that does not involve the ALU at all, but separate hardware which is just concatenating bits from different fields of the NPC and the instruction register together to generate an address. It does not involve the ALU or the other pieces of hardware directly, but would be done in this stage of the instruction execution. Okay, now moving right ahead. In the case of the load and store instructions, in the previous stage of execution we had talked about generating the effective address, in other words adding the base register value to the displacement, and getting the store data in the case of a store instruction. There was an additional cycle of work associated with load instructions in particular, and we will therefore separate them out into another formal stage in instruction execution which relates to the memory or cache memory, and I will refer to this stage as the MEM stage. What has to happen in this stage? In this stage, the work which had been done in the previous stage, in other words that of calculating the effective address and of giving the store data value, will have to be routed to the memory or the cache memory as the case may be. So the ALU output register contains the address in the cache memory or the memory that has to be modified or has to be read from. So if we are talking about a load instruction, then the ALU output value, which is the address of the identity in cache memory which is to be loaded into a register, therefore the address goes to the cache memory, and cache memory responds with a value which is put into a CPU register called LMD, or load memory data. So it is a special purpose register which contains the value which has been read out of memory or cache memory for subsequent storing into the destination register of the load instruction. So hence we show that the ALU output goes to the cache memory, and from the cache memory the data comes into a special purpose register called the load memory data register. If it's a store instruction, on the other hand, the ALU output will be used to identify which entity in the cache memory or memory is to be modified, and the B register will contain the identity of the value which is to be stored into that memory location, and therefore what has to be done is routing the value from the B register into the appropriate entity of the cache memory. So we show the path from the B register into the cache memory. So this is essentially something which takes an entire cycle, just like each of the previous diagrams did, and therefore we show this as one more stage of instruction execution. We have separated this out from the previous stage, which until now we had associated in the same sequence of events. Okay, so this is the activity that's going to happen in the memory stage. And finally, there's the last step which has to happen, the updating of the destination register, and in the case, this is relevant in the case of ALU instructions and involves taking the ALU output and putting it into the appropriate destination register inside the register file. There is also the need to update the register if this is a load instruction. You will remember that we have, in the case of the previous step, as far as the load instruction is concerned, we have got the data out of memory or cache memory into a special purpose register called LMD inside the processor. From there it must finally be routed into the actual destination register. So from the load memory data register into the actual destination register. And finally, if we are talking about a conditional branch instruction or a jump, the program counter value will have to be modified appropriately. So if the condition is true, as read from the condition register, then the modified the effective address can be routed to the program counter value. But otherwise, the new program counter, in other words, if the condition is false, then the NPC value, in other words, the instruction after the branch instruction will be the instruction to be executed, and therefore NPC value will be loaded into the program counter value. Right, so if we put all this together, this is what we get. We get all those simple pieces of hardware. This is the simple piece of hardware which was doing instruction fetch, the simple piece of hardware which was doing instruction decode. We have separated out the ALU functionality or the execute functionality from the memory access functionality. Hitherto, both of these were listed as two sub-steps in one step, but now I'm formally separating them out. And finally, the write back stage where the register file is, you notice that in the write back stage, a value goes back to modify the register file. We don't show the register file again, we show the register file as being a central entity. So from now on, we could refer to the 5 stages of instruction execution as instruction fetch or IF, instruction decode or ID, instruction execution or EX, memory access or MEM, and WB, which is an abbreviation for write back. So this is a simplified picture putting everything together. And you will recall that for some instructions, for example, for the jump register instruction, this piece of hardware is relevant, this piece of register is relevant, this piece of hardware is relevant, this piece of hardware is not, this piece of hardware is not, and this piece of hardware is relevant, which is why the amount of time to execute one instruction is going to be 3 cycles. And there would have to be some mechanism by which, if we wanted to, the jump register instruction would just execute in those 3 cycles. But for the jump register instruction, this piece of hardware and this piece of hardware don't do anything of relevance. Okay, so at this point we've actually come to a status checkpoint. If you look back at the agenda that we had for the course, we had a 9-point agenda, and by the end of the 10th lecture, we were supposed to have completed the first 2 points. The first 2 points were a description of program execution, something about compilation, object files, function call and return, address space. In other words, the way that the different entities like text, data, stack and heap associated with a particular program in execution might be arranged in memory. Data and its representation, in other words, the different kinds of data and how they are represented. In addition to that, the basics of computer organization, an understanding of how memory works, what registers are, an example of an instruction set architecture, and a good understanding of the basic ideas behind how instruction processing hardware is built. and we have achieved that objective in our 10 lectures. In fact, I'll proceed to move into the next topic briefly as to give you a rough introduction to the next set of topics that we're going to get into in the lectures that follow. Now, let me just do a quick reality check to explain why we do need some corrective action before we can say that we are in condition to understand how our programs execute. Now, if you look back at the hardware that we had, we have a situation where, and this is a clear description of what kind of hardware would be required for the execution of an instruction, and the instruction comes from a program. But if you think about it a bit, your experience is different from what this kind of hardware might support, because in your experience there could be many programs running on a computer concurrently. What I mean by concurrently is, for all practical purposes, at the same time. Right? There could be many programs running on a machine at the same time, and if there are many programs running on the machine at the same time, then we do need to make sure that the programs can use the same hardware at the same time, and this is clearly necessary, and we should not proceed too much further without understanding how that is possible. Right? Because if there are two programs running and I have to fetch an instruction for each of those programs, then I clearly need more than one program counter, because each of the programs we'll have to keep track in the hardware for each of those programs what the instruction of that program that is currently being executed is. Similarly, I will need two instruction registers and so on. So if there are many machines running at the same time, then the picture that we have in mind of the hardware might actually be unrealistic. Hence the need for a reality check, because as you all know, your experience with computers is that there are many programs running on the machine concurrently. Okay, now many programs that are running on the machine concurrently are sharing the resources of the computer. And what are the resources of the computer that they are sharing? They are sharing the processor. They are also sharing the main memory. In other words, if there are two programs running at the same time concurrently, then both those programs must be present in main memory. The instructions, the data, the stack, the heap of each of those programs must be present in main memory. Similarly, if there are two programs running, then the processor should be in a condition to execute the instructions of those two programs. Now, if there are two programs in main memory at the same time, then they must be protected from each other. Now, this is an interesting concept. And think about it this way. If I knew that there was a program of yours running on a computer, then I could run a program of mine on the same computer with the intent of doing something bad to your program. For example, if I knew exactly what address was associated with each variable of your program, I could write a program which would modify those variables. Right? So it's clearly going to be necessary to make sure that situations like this do not arise, because it is typically the case that there are many programs running on a machine at the same time, concurrently. Hence the need to make sure that programs are protected from each other. Right? This must explicitly be done. Otherwise, no one could safely run a program on a computer unless he had a guarantee that only his or her program was running. And that is typically not the case today, as you may be aware. Okay, so specifically, we must ensure things like this. We must ensure that one program in execution should not be able to access the variables of another program in execution. Because if it can access a variable x of another program, it can change the value of that variable x by simply doing a store instruction. Okay. Now, this protection of one program from another is typically done in terms of not being able to access the variables of the other program, is typically done through a mechanism called address translation. And we'll be seeing more about address translation later, but let me quickly give you an idea about address translation before we go ahead. Okay, now let me remind you that any one of the programs in execution is going to have its text, its data, its stack, and its heap. And therefore, as far as its use of memory is concerned, we had this picture in mind where its text, or by text what I mean is its instructions, might be present in the early parts of memory. In other words, memory addresses 1, 4, 8, etc. I use 0, 4, and 8 because the size of each instruction is 4 bytes. And we're sort of assuming that these are byte addresses. So the early parts of memory are the text. This may be followed by the data. This could conceivably be followed by the stack, and the heap could be at the other end. What is the other end? We could assume that the other end could be addresses. I mean, the highest address in memory might be 2 to the power 32 minus 1. If this is a 32-bit machine, the size of the program counter, the size of the various registers is 32 bits. This might be the size of the address space. The address space is the space of addresses, and the address space runs from, in this particular example, 0 to 2 power 32 minus 1. The size of the address space depends on the size of an address. So here I am assuming that an address could be 32 bits in size. Okay, now the idea of address translation is simply each program is written with this kind of an assumption, that it has an address space which ranges from 0 to 2 power 32 minus 1, let us say. And this picture is achieved by the compiler. Right? The compiler pushes the instructions or associates different instructions with these addresses. It associates addresses with the data with this kind of a picture in mind. So each program could be compiled to use addresses which are in the range of 0 up to the maximum address. In our example, 0 up to 2 power 32 minus 1. But these addresses need not be considered as actually being memory addresses. We could actually view them as being fictitious or virtual addresses. Remember, our objective is to try to provide one program protection from another program. And if we have this kind of a situation where the addresses that the program was written or compiled to use are not real but only pseudo or virtual addresses, then these addresses will have to be translated into real or actual main memory addresses before they are sent to the main memory or the cache. Okay. Now, if the translation can be done to ensure that one program cannot access the variables of another program, then this translation itself provides the protection that we were talking about earlier. So as long as the translation ensures that one program cannot access variables of another program, then we are safe. Okay? And then it becomes possible for many programs which are in execution to safely share main memory. Each of them will be using a separate part of main memory because of the way the translation is set up. Now the only problem here is we haven't talked about a piece of hardware which does that translation. And if the translation is not done by a piece of hardware, then it's going to make everything slower, because this address translation will have to be done through the execution of instructions, which is clearly a bad idea because it will make programs so much slower. Therefore, it must be the case that this address translation is done by a piece of hardware. And in terms of terminology, we refer to the fictitious addresses that are generated by the compiler as virtual addresses, and the actual main memory addresses that will be the result of translation as the physical address. So what translation does is it translates a virtual address into a physical address, and the physical address can go to the main memory or to the cache memory. As we have seen, this translation must be done by a piece of hardware, and we will refer to that piece of hardware as the memory management unit, and we'll abbreviate memory management unit as MMU. So that is the hardware that does the address translation. So this whole notion of making it possible for more than one program to be executing at pretty much the same time or concurrently makes this necessary, this whole notion of address translation and a piece of hardware to do that. So we now understand what that final block in the block diagram of the computer organization that we had seen was. The MMU is the piece of hardware that does the address translation. Just a little while back we had seen that the cache is the piece of hardware which makes it possible for us to make an assumption that most of the steps in instruction execution do not involve the main memory at all, and that only infrequently is main memory going to be involved in the execution of an instruction. Typically, the cache will provide the instructions and the data that are required by the program. So at this point in time, with this reality check, the net effect is that we understand more about why this yellow box is present. We'll be seeing a lot more about what the MMU does and how it does it, and with support from what kind of software. But for today, we have reached the end of our discussion of instruction execution. We have finished the first two line items in our agenda, and we'll proceed to the third and fourth line items of our agenda in the lectures that follow. Thank you.